So section 1.6 is titled Theory of Linear Systems because what we're going to do is dig a little bit into the theory behind some of the claims I've already made to you. First of all, we're going to prove once and for all that linear systems can only have one of the following: exactly one solution, no solution at all, or infinitely many solutions. There's only three possibilities. There's no other options that can happen. That's one of the things I'm now going to prove to you officially. Now, I did demonstrate this to you in section 1.1, but only in the specific case of a linear system with two equations and two variables, when we drew those three pictures, or three possibilities of two lines in the Cartesian plane. But now we're going to prove that this statement is true for absolutely any linear system. So that's probably the major result from this section. And we'll also consider a nice method for solving several systems at once if you happen to be in the unique and fortunate situation where all of your systems happen to have the same coefficient matrix, and that coefficient matrix also happens to be invertible. So that's really the ideal circumstance. So I'll show you a neat trick for that situation. And then we'll state a couple other results, but I won't get into that just yet. We'll get underway first, and it only makes sense to go over so much before we actually get started. So I want you to start by considering the following linear system. And it's going to be a system with two equations and two variables. And here it is. So we've got 3x plus 3y is equal to 6, and x plus y is equal to 2. Okay? And if you've practiced solving lots of linear systems at this point, you'll probably recognize this right away as one that's going to require a parameter to write down the general solution, and that's okay. But we won't actually go through those steps now. I trust that you can do that by now, and I'm just going to say I'll give you the answer right now, and you could take my word for it. If you want to check the details, go ahead and pause the video and check the details, but you aren't required to do that at this point. But let's say which has the general solution given by the following. If I write the general solution in column form, it's going to look like this. xy is equal to, well, y is going to be the one that you end up putting your parameter on of s, and then x will be 2 minus s. And of course that is where s is arbitrary. So where the real number s is arbitrary, just specifying that s is a parameter. Okay, so nothing new yet, but this is an example I want to say a few things about before we get into the theorem down below and its proof, because the theorem that's coming down below, this is the result I promised you, right? A linear system has exactly one of the following situations: no solution at all, a unique solution, so exactly one solution, or infinitely many solutions, and that there are no other possibilities. This is the big proof we're going to do down here. But some of the notation I use when I go through this proof might be a little bit intimidating, and it'll be helpful to be able to think of this example up here in mind when we go through it. So that's the purpose of this prelude here of what I'm doing. Okay, so I want to mention a few things about this situation. First, I can write down the matrix equation of this linear system. Let's call this linear system star. Okay, the matrix equation of star is going to be ax equals b, where we have to choose a, x, and b carefully so that this works, but let's do that now. So a, the coefficient matrix, is going to be the coefficients of all the variables. So it'll be 3, 3, 1, and 1. And then this x bar, our variable vector or variable matrix, is going to be consisting of the two variables x and y. And then what about our constant matrix B? That's going to be the constant terms over here, 6 and 2. Okay, so that's one thing you can do, is you can write down the matrix equation. And really, it's not even worth distinguishing now between a matrix equation and its corresponding linear system. They're both the same thing, just expressed in different forms. So quite often now you'll just hear me refer to this as a linear system, or maybe I'll refer to this as a matrix equation, because you can interchange so fluidly between each form that there's no point in being nitpicky about the distinction between them. Okay, and the second thing we can point out is that, well, by choosing values of S, we can generate as many solutions as we like, right? This is an example of a linear system with infinitely many solutions. Whenever you have a parameter in your solution, you know you have infinitely many solutions. So if you want to get particular solutions, you can just pick some values of S and start generating solutions. So let's do that now. I'm going to do that with two different values of S. So X, I'm going to write down a particular solution to the system. So I'm writing down the variable matrix, but I'm putting an index on it just to really, basically what I want to do is I want to write down now a particular solution. So I'm not going to write down variables here, I'm going to write down values that could be assigned to those variables. Okay, so here are the values. X bar 1 is equal to 1, 1. So in other words, that just means if I'm saying that this is a solution to this linear system, I'm really just saying that this linear system is satisfied when x is equal to 1 and y is equal to 1. And certainly that's true. Alternatively, I can get that by just looking up here at the general solution and choose s equal to 1. And if you choose s equal to 1, this is probably the most direct way to get this as a solution without having to check that it works for this linear system. Just plug in s equals 1. So you're going to get 1 for the second coordinate and 2 minus 1, which is 1 for the first coordinate. So this corresponds to the parameter value s is equal to 1. And then I'm going to write down another solution as well. And I'll call it x bar 2. And for this one, I'm just going to take s to be equal to 2. Choose the value s equals 2 for your parameter. Then you'll have 2 minus 2, which is 0 for the first coordinate for the x value. And then plug in 2 for s, and you're going to get 2 for the y value. Okay, so I've been rambling a lot, but what I really want to say is that for this second remark now, these are both solutions to star. In other words, this linear system. Okay, and what is the point of all this? The whole point of this that I want to point out to you is that there's another way you can state the fact that this is a solution to this linear system. We can just say that this is a solution to this matrix equation by just writing the following. Just write down this equation, but instead of writing the variables x bar, just write this matrix x1 bar. So we can write the following. We can write A x1 is equal to B and AX2 is equal to B. And this will actually work in terms of matrix multiplication too. This is a matrix up here, a 2 by 2 matrix. X1 bar is a 2 by 1 matrix. So a 2 by 2 matrix multiplied by a 2 by 1 matrix. The result will be a 2 by 1 matrix. And guess what you're going to get? You're going to get exactly this matrix B. So that's why it's correct to write this here. Same with over here. You can check that the matrix multiplication works. So this is another way of writing down solutions to matrix equation. You can write them down in vector form or column matrix form, right? So this is another way of expressing solutions to matrix equations. Okay, and this is going to be very convenient to do when you're working with a linear system where you don't always have access to information like how many variables does it have or how many equations does it have, right? So that's why this is useful to use this notation. So going forward, we're going to do that now to prove this theorem. So here's the theorem. I've kind of already read it, but I'll just go through it again quickly. A linear system has exactly one of the following. Only one of these three cases is going to be true at all times. You're going to have either no solutions at all, exactly one solution, or infinitely many solutions. So in other words, it's impossible to have a linear system that has exactly 2 solutions or exactly 3 solutions. That just never happens. As soon as you have 2 solutions to a linear system, you automatically know that you're going to have infinitely many. That's what this theorem is saying. So now how are we going to prove that? Well, we can't make any assumption. We want to prove it about every linear system, not just linear systems that have 3 equations and 4 variables, right? So that's going to make this challenging. So that's where matrix equations are really useful, because we don't need to worry about how many equations or variables we have. So let's say let AX equals B be a linear system. And let's say we've got two solutions. Here's the strategy. We're going to start with the assumption that we have a linear system, which we have written down right here, with two solutions that are different. And what I'm going to prove to you is that that automatically implies that this same linear system also has infinitely more solutions. And if I can do that to you, or prove that to you, then that is enough to justify this statement completely. So let's say that. So let this be a linear system with solutions x1 bar and x2 bar such that, and let's be really careful here, we want to rule out the possibility that we've just found the same solution and given it two separate labels. So we're going to say such that x1 bar is not equal to x2 bar if you compare them as matrices of values. Okay, well, now what we can do is make a new column vector. Because remember, these are both column vectors of values. Think of these as examples. Have these in mind as examples in the previous case. And you could think of this linear system here, you can just think of this as an example. It's not necessarily going to be equal to this system. We're doing a proof in general, but it's nice to have an example in mind just to have some intuition. Okay, so we're going to define a new column matrix, which I'm going to call x bar 0. So this isn't necessarily going to be a solution to this linear system. It's just something that we're introducing. Okay, and what we're going to set it to be is x2 bar minus x1 bar. If they're both solutions to this linear system, then they both are column matrices with the same number of entries, and we can perform this subtraction no problem. And because they're distinct, because they're not the same solution, this subtraction is not going to give us the zero solution. We're not going to get the trivial solution. So this is not equal to just simply the column vector consisting of all zeros, which is what I'm using this notation for. So really what I'm saying here is if I form this subtraction, I can define this new object x0 bar to be the difference of these two solutions, and since they were distinct, I'm not just going to simply get the zero matrix or the zero column matrix. Okay, so but what is this? What do you get if we define this? It's not actually necessarily going to be a solution to this system, but what it is going to be a solution to is the associated homogeneous system to this coefficient matrix A. And let's check that. Here's how you can check that. We're just going to calculate. Let me add another word to be clear. So let this be defined by this, which is not the zero vector, and then calculate the following. Let's just multiply x0 bar by A on the left and see what we get. Okay, so what will happen? Well, let's plug in what x bar 0 is. It's actually this structure here. So this is going to be equal to A times x2 bar minus x1 bar. And now the properties of matrices that we studied in section 1.4 kick in. I can multiply A by each of these two matrices separately and then subtract afterwards. So I get A times x2 bar minus A times x1 bar. And both of these are equal to B. This B bar up here, how do I know that? Well, we assumed right off the bat that we had a linear system with two solutions, x1 bar and x2 bar. So if I plug x1 bar in for x1 here, I'm going to get B bar. And maybe it's worth writing this out separately. Note, I got some room over here. Because x1 bar and x2 bar are solutions, we have A times x1 bar is equal to B bar, and AX2 bar is also equal to B bar. This is what it means for these to be solutions to this linear system, right? Again, think about this as an example. We had two solutions to this linear system, or this matrix equation, so it turns out that these equations hold. So it's no different down here. The only difference is we just don't know what any of the values are because we're staying general. So, but the point is, this is equal to B and this is equal to B. So you get B minus B, which is equal to 0. Okay, now what is the conclusion? Therefore, let me add it in over here. Therefore, A times x bar 0 is equal to 0. In other words, what we're saying here is that this new matrix that we've defined over here, which is really just a bunch of values that we can assign to the variables in this linear system, this is going to give us a solution to the associated homogeneous system over here, and that's what this is saying here. But then we're going to use this in our next calculation. Okay, and my claim to you is here's how we're going to generate infinitely many solutions to this linear system here. So the claim is that for any real number t, this is essentially the parameter, because somehow you have to get a parameter in a solution, in a general solution that has infinitely many solutions. If you don't have a parameter, then you don't have infinitely many solutions. But here's how we're going to generate it. So watch what happens. If I were to take A and multiply it by x1 bar plus t, which is, so I'm just going to add some multiple of this new x0 bar that we've created. Okay, so what happens if we work this out? So you can see I've taken this up here that we defined at this stage, and I've plugged it in here, and I multiplied it by some arbitrary parameter t, and then x1 bar, that's just the first of our two solutions that we originally started with. Okay, let's carefully work this out. This is the key idea here. So we're going to get a x1 bar plus a times tx naught bar, right? Just using the distributive property of matrix multiplication. Now, what's this going to be? This is going to be b, right? Just like this was b here, this is going to be b again. So we're going to get b, and then here I can pull this scalar. T is a scalar, right? A is a matrix, x naught bar is a matrix. T is a scalar. I can pull it out front, so I get plus t times a x naught. And what is ax naught? Well, we already showed that that's equal to the zero matrix, right? So a column matrix consisting of all zeros. So we get b plus t times the zero matrix, which t times the zero matrix is just going to be the zero matrix. So if you go b plus the zero matrix, you're just going to get b. So what that means is we've just generated another solution, but for any value of t. This is a solution for any value of t to the matrix equation ax equals b. Because look what happens. We went a times this expression here, and what did we get when we did finish the calculations? We got b. So hence, this is a solution to this linear system for any value of t. And we don't really need, that's actually more than we need, because that's going to give us even more solutions than we need. Just restricting yourself to the case where t is equal to the positive integers is enough. So here's what I'm going to add. Say now, taking t equal to 1, 2, 3, and so on, just taking it to all those values, we get the solutions as follows. You get x1 plus x naught. That's what I get if I take t equals 1 in this expression. X1 bar plus 2x naught. That's taking t equal to 2 in this expression. What about the next one? X1 bar plus 3x naught, and so on. Really what we're going to get is an infinite list of solutions. So let me finish, add some more words in up here. We get an infinite list of solutions. So how is it infinite? Well, what would the next one be? x1 plus 4x naught, x1 plus 5x naught, x1 plus 6x naught. If I could keep going as long as I wanted, if I want 100 solutions, I'd go all the way to x1 plus 100x naught. I can just keep adding this column matrix that we've introduced over here, x naught. I can just keep adding that over and over and over again to get a new solution each time. And how do I know I'm not just generating the same solution over and over again? Because that x naught is non-zero. That's another key reason. Because this is non-zero, that's how you know that all the solutions in this list that I'm not going to write any more than this, but this infinite list, you know that they're all distinct because x naught is 0. So let me add that in, which are distinct since x naught is not the zero matrix. Okay, so that is your infinite list of solutions. Okay, so finally we can say Well, that completes the proof because we've proven that there's an infinite list of solutions. So I can draw my box here now and know that I've finished the proof. And let's recap on the logic to clarify why is it that I can say I'm done, right? We wanted to show that a linear system has exactly one of the following attributes. It either has no solutions at all, a unique solution, or infinitely many solutions. And what I said at the beginning was this is equivalent to saying the following. As soon as you know you have two distinct solutions, you automatically have infinitely many. So that's how we started, by saying, suppose we have a linear system with two distinct solutions. That's what the second line here was assuming. And then everything after that was work to demonstrate that then, based on that assumption, we can conclude that we have infinitely many solutions, which the list, if I were to keep on writing this list, it would be infinitely long. And all the values, all the solutions would be distinct. Since our x0 bar is not the zero matrix, that's how you know that the proof is complete.